So first of all, I'd like to tell you that I tried to find information on whether you can get MATLAB now as a COVID-19 license, but unfortunately I couldn't find this information any longer. So I have added a link to Octave, which is equivalent. It of course lacks many toolboxes and some additional tools like Simulink, but for our needs it's enough. Yes, we can use that. So you can download it here in a course description to make your practical works. That would be about software, which we will use for practical exercises for your study project, and you can also use it for exam exercises, which you will have 2 tasks and 1 theoretical question to answer. This will all be done in a remote manner, so you'll have a lot of time to do that. But okay, we now start our lecture today, and we should talk today about some mathematics of the signals, of description of those signals. That includes both mathematical expressions and geometrical interpretation, which is more intuitive, and so we will talk about that. Last time our lecture was finished with a digital communication system, and I showed you why digital communications are superior to analog communications if we are talking about noise. That was because we could regenerate a signal and recover its form. However, we have touched very briefly how we should convert analog signal to digital signal. If you remember, during our first practical exercise last lesson, when we had work in Octave, we converted our digital symbols 1 or 0 by simply repeating them for 100 times. Yes, that was our, let's just say, way of making converting digital signal to analog signal in software, of course. If we had the opportunity to use a hardware, we would use a real component which is capable of doing this, and we would see sample on the oscilloscope. However, we were limited to using software, so we had to create a model of this analog signal. And we used 100 repetitions of each value. Yes. So today I'm going to tell you how many times do we actually need to read from this signal to convert it back to digital, in order to ensure that we will not lose any information in the process. That is of the highest importance to us. That will be the first part of our today's lessons. The second part will be more related to complex signal description, and I am hoping that I will be able to give you both clear, intuitive insight into this thing. Yes, we will use geometrical representation. We will draw them as a vectors and see what happens during a transmission, and also some mathematical background to this topic so that you can read literature. That is our plan for today. So let us begin. And if you remember on our first lecture, when we talked about a little bit, we talked about analog to digital converters, we have skipped the question of how often should we make sampling of the analog signal to convert it to digital signal. Yes, so that is the first operation we make for our analog signal to make actually a digital signal. So here we can see discrete samples of this analog signal. I'd like to remind you that discrete signal is not really equivalent to digital signal. It's rather intermediate form of a signal. So an analog signal, we have, let's say, voltage here, and we have a continuous function which exists at any given time moment. Let's just say it's dt, which is as little as we'd like. Contrary to this, discrete signal is still represented as a voltage, but it is taken at a certain time intervals with some fixed and finite time of sampling period. Yes. Then we have a digital signal, which is no longer a voltage, but a binary code, which encodes each voltage level, also with a sampled time. So we are talking right now about the first step of reading samples from the signal and how often that's done. And the mathematical model is very simple. We basically multiply our signal with finite time pulses, yes, which are following with a fixed time step. Well, to be more precise, you actually don't have to take a fixed time step. However, in many practical applications and considerations, we would like to know exactly when our next signal value will be. And variable time step is also possible, especially if we are talking about some signals which behave very differently. So you can see here, for example, we have a very fast signal which must be read more often. Yes, we need to take more samples in this segment of the signal, and we can take less samples less often, those samples in this signal. However, this is mostly purely theoretical question, and those are theoretical studies, as it's quite difficult to use it in real systems, such signals. So here is such a, let's just say, a comb of delta functions which are shifted or translated by 1 period, 2 periods, 3 periods, and so on. And we just multiply our signal. And here, between those delta functions is a 0 value. Yes, so basically our signal is nullified between those samples, and we obtain this discrete sequence of the samples. So it's very simple to achieve. Now, there are a few questions we must answer. First of all, what is the correct choice of this sampling time? Obviously, we could take two short time interval, we could take two long time interval, and what is the optimal value of this time step? Well, that question is not so simple to answer, and it often is very dependent on what application we are talking about. Therefore, we have to choose our value in each case separately. However, there is still some fundamental limitation of what value we should take at least. So we are talking here about lower bound, that there exists a lower bound which we cannot, well, we can't take less than that bound. And application-wise, it's more related to the upper bound. So basically, as long as we satisfy the lower bound, we can choose whatever upper bound we'd like. So why is this so important? This is so important because the information contained within that signal, as we were talking about in our first lecture, is contained in the entire signal, in this signal. And if we take that signal, read that signal too roughly, let's just say, we risk losing some of this information and losing it without possibility to recover it later on. So for this case, well, that signal looks fine if we sample it like this rather than this. This is too precise description of the signal, and we could actually do well with this description. Probably, yes. However, if we are talking about signal like maybe some sine wave, which we would sample like this, for example, we take a value here, we take a value here, we take a value here, then obviously, if those points are only thing we have to know about the signal, there is no way we could imagine that it was actually a sine wave. Rather than that, we will assume that it was some constant level. And as you can see, our signal has not been reconstructed successfully. So we need to sample signal with some sufficient frequency in order to be able to recover all the information from that signal. What is this sufficient frequency? Let's take a little example. Consider some free-form signal which is sampled with a fixed time period. So after we perform this sampling, we lose any information contained between those samples. So basically, blue line goes away, and all is left, everything we have left is those samples which we are using to try and recover that signal. That signal hasn't been monotone in each segment. So for example, here you can see that it was increasing and decreasing. Yes, also it's like here and so on. So we cannot really use just simple straight lines to recover that signal. We are using some different approach in order to reconstruct. Of course, this is also possible, and well, maybe technically not so easy to achieve, but the form is still closely related to the original form. Still, we can, in this case, perform a perfect reconstruction of this form. How is it achieved? If certain conditions are met, we will talk about these conditions right now, it is possible to recover the lost information if we replace each of the samples with this function, which is basically sine x divided by x function, the first limit, which is close to 0, if x is close to 0. Yes, that is that function. And this function is this line what connects those points. So basically each of those points, each of those samples is replaced with this function. So for example, you can see here, yes, that here is this function. I am trying to draw it here because maybe its color not so clear in conference. It should be better in video uploaded at Tortoise, but currently I'm assuming that you may be unable to see that. Yes, so I've drawn it maybe not so perfect as it was. Still, the idea is clear. So after we are doing that procedure for each of those samples, we can see that actually the values in between will be different, and they will be a sum. Yes, they add up to a constant level. So for example, we can see this function here giving us at the middle point this value. We have also this function here, and yes, another thing is that sine x divided by x function is scaled in its amplitude by the value of the sample. So for example, if we have here 1, then we take 1 sine x divided by x, yes. If we have here minus 3, then it will be minus 3 sine x divided by x. So the amplitude is kept, yes. And we should just add those points together. Now we can see that here we have like this, yes. So we add up this value on top of already collected. Now there are also some negative values and some very little positive values. So basically we'll have something like here in total, yes. And as you can remember, there was actually a maximum of this function. Well, maybe not full maximum. No, I believe it is a full maximum, no higher value for this. So after we add up all those lines together, we reconstruct our signal and we do it perfectly. So this signal is basically the same signal as was in the beginning, and we didn't lose any information after we recover that signal. That has been possible only because we have chosen the correct time step, which is closely related to the spectrum of the signal we wish to convert. So in order to know what is the correct time step for this signal, we have to calculate its spectrum by using Fourier transform as omega. After we draw that spectrum, we can select appropriate sampling frequency. And sampling frequency is a reverse value of a sampling period. So let's say sampling period is here, and the frequency will be 1 divided by, no, I mean the period will be 1 divided by the frequency, and vice versa. If we want to find frequency, it will be 1 divided by period. So if we have this frequency, we will have this period as well. And it turns out that according to the sampling theorem proposed by Nyquist, the condition of a perfect reconstruction is the correct choice of this sampling frequency. So this sampling frequency must be at least double of the maximum signal frequency in the spectrum. So that is why we need spectrum to find out what is actually the highest frequency used by our signal. Now, of course, you can tell me that actually spectrum is infinite. That is true, but often in practical considerations, we are drawing some limit and evaluate, for example, total energy of this part, yes, of this band, frequency band, delta F, and, for example, ask it to be at least, let's just say 90% of the total signal energy. So we are keeping the most part of the signal energy, and we are sacrificing only 10% of these actually very low values. Yes. So again, this limit of the frequency band is also questionable for each application, and we will talk about it later from the perspective of digital communications. What is this limit, or what is this frequency band required to send data with some specified data rate? But currently, we are just assuming that we have found it via one or other criteria, this frequency, and so we can choose the appropriate sampling time interval. So in this case, for example, we have a signal of 50 nanoseconds rectangular pulse. So duration of this pulse is 50 nanoseconds. Yes. This is the spectrum of such a signal. Now this is a separate pulse. This is not a periodic signal, so that's why we use integral Fourier transform to calculate the spectrum. Yes, minus infinity, plus infinity, and signal which we would like to calculate spectrum for, and base functions which we are using to describe our signal. So we find spectral density according to this formula. And basically, if you calculate this for a rectangular pulse, you can specify it. Of course, it exists from some beginning time and has durations of 50 nanoseconds, which would actually be our real limits, which we will input here in this integral. And then our signal value here is some voltage. Let's just say, for example, 1 volt. So it's constant, and integrating this exponential is rather trivial task. So you could integrate it, calculate, and obtain the result of basically sine x divided by x type function. And you can see that actually we are drawing an absolute value of this function in this plot. So I hope you already know that, so I'm just repeating it to remind to you. And yes, so we have selected our maximum frequency, and now we need to take and find the appropriate sampling time, appropriate from the point of view of minimum value. So what is the minimum value of sampling time period we need to use for such a signal? So given that the sampling time is a reverse of the sampling frequency, we obtain value of 5 nanoseconds, which means that our rectangular pulse of the 50 nanoseconds will contain 10 samples. 1, 2, some here as well. That makes 4, 5, 6, 7, 8. Well, I didn't divide them with a fixed time interval, but of course here must be a fixed time interval. So basically that would be for this frequency, yes, the appropriate sampling time. Do we actually need to take that limit here is questionable. Yes, if we are talking about communications, then probably not. We would be quite fine if we take, for example, that maximum frequency here. Then again, if we are talking about some medical equipment, about cases when we actually care to keep that pure rectangular form, then this may be also not enough. So this purely depends on the task at hand. Yes. So what happens to the spectrum after we convert signal from an analog form to digital form? Basically, there is one simple thing, that spectrum becomes replicated. How it happens? So here is our selected maximum frequency, which is also called a Nyquist frequency. And here is our sampling frequency of twice as much of this Nyquist frequency, at least twice as much, yes? So basically, the spectrum here is very same as here, and here, and here, and so on, up until infinity. So the spectrum becomes a periodic function. Now, if we watch what happens here, then we have actually a mirrored spectrum, yes? So basically, they are like symmetrical to this axis, with the exception that actually here we can see an absolute value. So we don't know about sign and phase anything, but in reality, spectrum is a complex value, and this part, these two parts have a different imaginary part, so they are complex conjugate parts. Yes, basically that is the only difference in those parts. And we actually can wrap this spectrum around a circle. So imagine that we take it as a sheet of paper and try to roll it. Yes, and this way we can use a so-called Z transform to perform this operation mathematically, which is also quite often used in discrete time systems and filters and so on. Basically, this spectrum part is represented here in the circle of the Z plane. And you can see here is Nyquist frequency matching pi, and sampling frequency matching 2 pi, 4 pi, and so on and so on. So we could take circles infinite times here, yes. So we have some ending to this spectrum, which can be seen also here as we get closer to our sampling frequency divided by 2, which is Nyquist frequency. Our amplitude of the signal decreases, and then again it's like a mirror here, which is once again interesting thing. For example, consider this spectral component of some frequency f1. The thing is that it will be the same as here due to a very simple fact that basically you could, let's just mark this component here, like somewhere here, I think, yes, on this circle line, which matches the opposite rotation direction by this angle. So they are mostly the same, and that is what, let's just say, prevents us from a perfect reconstruction if we choose our limit frequency purely. So basically we need to choose that correctly. We'll talk more today about this complex representation of numbers. Here we use a complex plane, yes, real part, imaginary part, and unit circle. And we will speak about that a little bit more. We will not talk about Z transform in this course, however, so I hope you have some information about that, or you could always also look at Wikipedia and some books, yes, for this topic if you are in a further need to know something more about this, maybe for some of your study project or something like that. So also you could ask me questions then if you have some specific questions. So basically we have here watched what we need to do to make that lower bound, but we could also take more than that or less than that. So this leads to additional cases. One case is a perfect match according to this theorem condition. We take equality, yes, not more, but just equal. And this is the minimum case. Now we could take more or less. So if we are taking samples rather less often, let's just say so. So the sampling time period, time interval is longer, and we make less of those samples. For example, if we chose instead of 5 nanoseconds, 10 nanoseconds, then for our case of signal of rectangular form, it would also be sufficient. If we have only 5 samples, each of them with 10 nanoseconds. Yes, this is called undersampling. So we basically intentionally reduce the sampling frequency to reduce amount of data, because we need to account for that each sample actually contains a binary code which we need to send, process, code, and do all the stuff we have talked about in the first lecture. So basically, this is the this influences the volume of information we'd like to send. So the more often we take those samples, the higher this volume, the more data we need to send, and the longer it will take. Then again, if we need absolutely precisely to describe the signal, very often we are doing this in the computer simulation software such as Octave, and that is what we did in our first practical work. We actually just oversampled that given signal and well, replaced each value with 100 values. So that oversampling ratio in our case has been 100. Here, this oversampling ratio is 5. Yes. So in this case, we will take more samples than needed, but this will improve the accuracy of the signal description. And accordingly, those are procedures of getting such signals called downsampling and upsampling. Basically, these operations are performed with already discrete signal. Yes, so basically, for example, consider that you have performed this sampling and then you decided that you could actually take a longer step. Yes, you cannot take shorter step here now, but you could, well, at least not so directly, but you could always skip some data. Yes, for example, let's just say we skip each second value. This is called downsampling. As for upsampling, we will have to actually find some way average value. So basically, this is performed by converting signal to this analog form by using sine x divided by x function and then resampling it. So basically, we, well, maybe do not need to actually convert. Yes, since we have this function and we know this function for each sample, we could calculate it rather than perform full conversion. But still, this is the approach to go. So basically, it is possible to try and reverse. Of course, if you have selected your first sampling frequency correctly. Now, if we have performed oversampling, then there is nothing bad for us. With the red dots, you can see the minimum required sampling frequency, sampling period, yes. And with the black dots, the oversampling data. So basically, if we connect with sine x divided by x those points, in both cases, we will get the same signal and no problems here. Now, however, if we perform undersampling and we read our samples less often than is required, then we will have a problem. And this problem is called the Elysing effect, which basically will lead to incorrect reconstruction of the signal. Let's see if I have. No, I don't have here. So what we will get is the signal of the following form at much slower frequency. We can tell what exactly this frequency will be because it matches the case when our spectral component was here. So basically, our frequency will be mirrored, and we will see it as another frequency. Not only we will see that as another frequency, but it actually will be that another frequency. So this can also work, of course, both. Well, not really can work both ways because we can't really from those 2 points get this information about this and this. Yes. We assume that the function is more or less monotonic in this segment. Yes. So this only works one way. So what is this Elysing effect? This Elysing effect occurs if there is such a situation that in our original spectrum, here was something else. Yes, we had some spectrum left unchecked, and actually we have drawn this limit here and didn't thought about what would happen with this part of spectrum. In reality, what will happen is that it will be mirrored inside here and add up to our spectrum and will, of course, well, damage it. So basically, this mirroring process is called Elysing. Yes, and that is a bad thing. We could always use a filtering process to avoid such thing. So basically, when we are talking about analog to digital conversion, we actually need to use a filtering before we perform this conversion. What is filtering? Filtering can be considered as such a case of a spectral mask. So we say that we want to keep here spectrum. As for this part of the spectrum, it's undesirable, and we try to attenuate it as best as we can. Well, this, of course, depends on the filter type, but filter just performs a frequency selection. So it's frequency selective filtering. It just decides which frequencies are left and which not. So basically, it's an amplifier with a varying amplification parameter depending on the frequency. Yes, and we specify our spectral mask to actually describe what we need. So if we use this filtering, this basically eliminates this undesired spectrum part, and we no longer suffer from this Elysing effect. So I'd like to show you a little demonstration or visualization of this Elysing effect. The example is very simple. The video camera is also a digital device which converts our analog reality by filming it into frames. And each camera has its specific number of frames per second, 60 frames per second, for example, yes, which is actually our sampling frequency. That is how often we are taking information from our world. And what happens if the information is changing faster than that in the world? What we will see in this case? Well, maybe you already know that in some cases we can see that the rotation direction changes, but I'd like to show it now as well, which you could also see by clicking that link. So here is some explanation. I will mute it down now. The idea is very simple. We basically connect our motor and this wheel to this motor connected to a generator, which can, let's just say, increase rotation speed. Yes, so we basically will from now on only increase the rotation speed, and we'll see what happens with that ring, with that wheel. Yes, so it's rotating counterclockwise right now, and we have marked this with this blue strip. Yes, the position, which is easier to see because, well, those lines, yes, are exactly what will make an illusion of rotating in different direction, because they have some specific angle between them. Yes, and if it turns out that, for example, let's just say, I don't know what is exactly angle here. Let's just assume that it's, let's say, 20 degrees. Yes, so if our wheel turns between two frames for 19 degrees or 21 degree, it will be roughly the same. No, roughly it will be the same value, but in different directions. Yes, and there is no such problem for this marking because it has entire 360 degrees to compare with. Yes, so what will happen now is that we will increase the frequency of rotation, and we'll watch what happens with that ring. So we basically just increase, we do not decrease. So it should start rotating faster and faster, but you already can see that the red strip and the white strips are rotating in different directions. Now white strip stopped, and now they again rotate in the same direction. So yes, that happens when we are closing to Nyquist frequency. After we cross the Nyquist frequency, rotation direction is changed. And since the spectrum is periodical, as we increase our rotation speed, we yet again and again change rotation direction. Well, rotation direction actually in real world doesn't change. Our camera limited frame rate makes us see that it is. Yes. So basically this is the effect of Elysing, or the insufficient sampling frequency for this case. Now this wouldn't have happened if the rotation speed of the wheel would be constant. Here we have this problem only because we actually have a constant acceleration. Yes, so we have a constant acceleration, and well, you can see here that actually we have already achieved so high speed that it's actually almost nothing to see here. But then again, you can see those lines still change direction, even at this high speed. We already cannot see that red strip and blue marking, yes, because it's rotating that fast. So basically, this is a good visualization of what happens to signal if we choose our sampling frequency incorrectly. We can actually misinterpret that signal. We could understand it incorrectly. Yes. So we have talked about this, and since we have talked here about rotational movement, we have slowly came to complex numbers and circle and complex plane and so on. This is a, I think, good transition point. Yes, because, well, actually a lot of natural processes such as heart beating, movement of planets, and so on can be described as harmonic processes. Yes, as a sine wave or cosine wave. And basically, those harmonic processes describe movement in a circle of some object. And we have also, of course, Euler formula, which can be used and which we will use in the second part of our lecture today for mathematical description, and also to describe geometrical description. So basically, we can put those harmonic signal on axis, on x-axis, on y-axis, and in school trigonometry formulas you have already done that, but we will see that today a little bit from other perspective. And so yes, here is, as we have learned in school, x-axis is a cosine and its real part. And however, please note that actually we are describing how this point moves on this x-axis rather than, well, what I'm trying to tell is that we have here in this vertical picture cosine and the real part rather than imaginary part. Yes, because this is actually a, well, let's just say some time, some projection in time dimension of what happens with signal on this axis. So basically, what we could see if we would be in two-dimensional plane is that this point moves along this axis. And this is a picture how it will move if we are, for example, moving this away from us. And the same is for y-axis. Yes, so here is the sine function. And basically any complex number, according to Euler formula, can be represented as a vector, yes, with amplitude A and some phase shift, which is actually, well, contributed from the entire this expression. And of course, if we have quite high frequency f, for example, gigahertz, megahertz, then most often we take into consideration this initial phase, because basically here is 2 pi times some great number, which still gives us a fixed number of circle rotations, yes, and everything that matters is this remaining initial phase. This is for x and for y, yes, so real part is this projection, and imaginary part is accordingly this, this projection, yes. So we will use that fact later to describe some unwanted effect in operation of receivers for telecommunications, which, well, unfortunately cannot be avoided as they are and require from us some advanced mathematics to use, but we will talk about it on the next part of our lecture. Let's just complete some introduction to the complex signals. Yes, so I assume that you know already a lot of complex numbers, such that we can calculate an absolute value of this number, yes, by well, calculating real part squared plus imaginary part squared and calculating square root of that. That we can also calculate the argument, yes, by calculating arctangents of the imaginary part divided by a real part. That is a school program, and I'm assuming that you, well, at least can remember that and or know where to watch it, and that this information is well, easily available to you. So we are more looking at this point to actually use that in Fourier transform. If you remember, I was writing here a formula and we had a complex exponential base functions in that Fourier transform. Yes, so for different omega, which basically in analog signals is changing with a very, very small step, arbitrary small step, yes, which can be actually close to zero. And there is a lot of those sine and cosine waves combined together into these let's just say spirals. Yes, so if we watch on this, add up to this picture a third dimension at time vertically, yes, so this would look like a spiral. This signal is actually spiraling, and projection on real axis would give us cosine, projection on imaginary axis would give us a sine function, yes. Likewise, we can describe cosine and sine function with these Euler functions. Yes, so if our Euler function here is like this, yes, and we substitute our cosine and our sine into that function, then we will actually get indeed this value again, and we'll basically have an equation like this, yes. So that holds true in both directions. So we can both express complex exponential via harmonic function, and we can also express a harmonic function as a sum of complex exponential. And basically, well, we haven't talked about vector representations yet, but we already talked a bit about spectrum. So basically, this means that each of these components, so not this one, represents this delta function in a spectrum of this signal. So if we calculate via Fourier transform spectrum of the signal, we will have two components. Each is only a half of actual cosine amplitude. Yes, if we have here one amplitude of cosine, then each of these will be only half. And also we have this as a negative frequency. This is an abstraction, of course. There is no such thing in real world as a negative frequency of the process. This is a mathematical abstraction of the Fourier transform, which nonetheless is, well, at least can be in certain conditions useful. I will try to show you at the end of the next lecture what those conditions can be. And well, maybe you will believe me that in some cases we'd like to use this form of a signal rather than this. However, in other cases, it's well, it's opposite, yes. As for sine function, and it has different imaginary part, sines, yes, for those components. But basically, it also is represented as a sum of two base complex exponential functions. So these are those base functions which were here in our, well, I will also put here I, yes, rather than j here, yes. So basically, for this specific frequency f0, only there is a common energy only with these base functions, which are, of course, a case, separate case, some specific case of this more universal expression of a base function. So basically, when we calculate our Fourier transform, I will once again return to this formula after all. We are just attempting to check each possible base function. So it's very similar to series, yeah, Fourier series, but only with infinitely small time step and frequency step, I omega t. T integral minus infinity plus infinity, and this is our spectral density. So we basically try very different frequencies. We take one omega value, calculate, and find how closely those are correlated. If there is in our signal S this value, yes, so basically we can always, for example, just put inside this, assume that our signal S is this sign, yes, put that inside, separate it to make those two integrals. Integral, the sum is the sum of integrals, and once again those are complex exponential, which will be rather simple to integrate, and that will give us the answer. Yes. So basically we will later on once again recall to this result, but for now I think we could make a break. We have already been talking about an hour, and it will be additional difficult material at the end of the next lecture, so I don't want you to feel very tired. So I think we can make a break of, let's just say, 17 minutes, yeah, and continue at 13:50. And that will be our last lesson today. We will not have a practical work today because, well, as I have already told you, we are not quite ready for it, and we will have more theoretical knowledge later. And well, I could give it today, but I think it's better to first tell you theoretical meaning and then to see how we can actually simulate it and so on. So well, thank you. Let's make a little break and we will continue at 13:50.